Hypertrophic cardiomyopathy, or HCM, is a common heart disease in humans and cats. Myocardial disarray is a classic feature of this disease and is characterized by a disorganized and bizarre orientation of the myocytes. Histology is the gold standard to detect myocardial disarray. We evaluate the accuracy of micro-CT for myocardial disarray by direct comparison between histology and micro-CT in cats with HCM. We perform micro-CT scans in normal and HCM hearts and assess myocyte orientation using structure tensor analysis by determination of the helical angle and two other variables, namely myocardial disarray index and fractional anisotropy, where values close to 1 represent myocytes aligned in the same direction, and values close to 0 represent random myocyte orientation. In normal hearts, there was a smooth transition in the helical angle across the heart walls and higher disarray index and fractional anisotropy values, while in HCM hearts, the areas of disarray on histology represented disruption of the helical angle and lower disarray index and fractional anisotropy values, shown here as darker areas in the color maps. Our study suggests that micro-CT can quantify myocyte orientation and detect disarray and can be used in the diagnosis of HCM.
My name is Jenny Romell, and I will show you why phase contrast CT is great for imaging mummies. Mummies and other human remains can tell us about ancient societies and religion, but also give insights into what diseases were common in ancient times. Imaging methods such as histological analysis, MRI, and of course absorption-based CT can be used to examine mummies. But when it comes to imaging soft tissues, they all have their flaws. We propose that we instead use X-ray phase contrast CT for non-destructive acquisition of high-resolution 3D data of ancient remains. So what new information can this give us? We have demonstrated this kind of imaging on a mummified human hand using our tabletop system, and I will show you some of the results. Here you see a virtual section through one of the fingers. Surrounding the bone, there is the hydrated soft tissue, which we can capture in remarkable detail. We can study the microanatomy of the soft tissue and, for example, segment blood vessels and even detect the remains of individual adipose cells. This proof of principle study opens up for completely virtual histology of mummified soft tissue, further decreasing any need for destructive imaging methods when examining ancient remains. We will continue to develop this technology in our spin-off company, Exiscope, so if you're interested, please visit our website. Thank you for your attention.
The skeleton of sharks and rays is formed completely by cartilage. However, despite the gelatin consistency of cartilage, their skeleton is still able to perform all functions that a bone skeleton can do, including dealing with high impacts. This is because their skeleton actually does mineralize, but just at the surface, forming a thin layer of about 100 micrometers thick. This layer is called tesserae and is formed by thousands of tiles joined together, giving the impression of a mosaic. In this cross-section, we can see small spaces within the tiles. In those spaces, there are cells living inside. The objective of my project was to study how the cells are arranged inside the tesserae, and for that, we scanned several times with synchrotron, and then, with a mirror, we segmented those spaces where the cells live. We discovered that each tesserae contains thousands of cells, and they present different shapes and orientations. Different shapes are associated with specific locations. For example, rounder cells are located in the middle of the tesserae, while more elongated cells are in the periphery. Actually, these elongated cells show a specific orientation, being aligned in strings oriented toward the neighboring tesserae. This arrangement could be related with biomechanics, but also with communication, where the cells share information among the tiles. This indicates that the cells actively maintain the skeleton of sharks and rays during all their life, allowing them to perform all functions, including jump out of the water.
Hi, I'm Lauren Wern from Flinders University, Adelaide, Australia. This pilot study is part of a larger study aimed at performing mechanical testing of bone implanted with press-fit prosthesis. Here we assess the zero-strain errors obtained by digital volume correlation, or DVC, in 4 plausible scanning configurations, using a cabinet micro-CT system for a human tibia implanted with a titanium press-fit tray. The configurations are in air, being ideal, then an aluminium cylinder of 2 mm thick walls, as used previously at the synchrotron for mechanical loading, and in both cases for 2 rotation steps of 0.11 and 0.18 degrees. One cadaveric proximal tibia was resected, implanted, and micro-CT scanned at the 4 configurations, with repeated scanning and repositioning of the tibia at each. 9 cubic volumes of interest of 13 mm side length were selected, containing either bone or centered on implant pegs with surrounding bone. For all scanning configurations, the mean absolute errors were comparable and furthermore were below 525 microstrains, with 264 microstrain standard deviation, which is within the range deemed adequate in literature, being less than 10% of the yield strain of bone. This study will continue, aimed at performing mechanical testing of bone with implanted press-fit prosthesis.
Hello and welcome to this quick overview of our advanced reconstruction technologies for Zeiss X-ray microscopes. This is a smartwatch battery. On the dark regions, these are the anode layers, the light regions are the cathode layers. One of the biggest challenges when performing non-invasive three-dimensional imaging on these samples is that of speed. If you want to do in situ studies or multiple interior tomographies, a lot of times that can be impractically long in acquisition time. If you wanted to push speed on this kind of using a traditional filter back projection algorithm, say from this 24-hour scan to a 12-hour scan, you'll end up improving or increasing noise in the reconstruction in an unacceptable way. To combat this, we can use a range of different advanced reconstruction techniques. We have our OptiRecon technology. This is an implementation of iterative reconstruction on our X-ray microscopes, and that allows for an up to 4x improvement in throughput without a significant degradation at acceptable image quality. Or we can use Deep Recon, which is an implementation of deep learning for reconstruction, and that allows for an up to 10x in throughput improvement at acceptable image quality. So that allows us to push down scan time without degrading our image quality in the reconstructions. Once again, we have OptiRecon and Deep Recon. OptiRecon is iterative reconstruction, Deep Recon is deep learning for reconstruction. If you have any questions, come by the Zeiss microscopy booth and ask them, and we're
Hi everyone, today I will be discussing in brief the effects of fluoride on enamel remineralization through X-ray microtomography. In order to achieve this experiment, 1/2 half of the sample was first subjected to 4 days of demineralization followed by a week of fluoride treatment. It was then immersed in artificial saliva at pH 7 for about 56 days. The present slide shown here depicts magnified version of the same tooth half, in which the line profile is drawn through enamel surface and subsurface to analyze mineral density changes. The corresponding graph for the same depicts fluorapatite layer formation at the enamel surface, which may prevent diffusion of ions from the artificial saliva into the subsurface and slows down the overall remineralization rate. The XMT scan of the second half of the tooth sample was also subjected to initial demineralization. However, it received absolutely no fluoride treatment and was immersed in artificial saliva instead. The corresponding graph now shown here depicts how without any fluoride treatment an almost complete remineralization of the enamel subsurface can be achieved. So I hope you found my results interesting and thank you for being here.
Hello, my name is Elaine and I will be speaking on optimizing X-ray microcomputed tomography for routine histology. Histology is the study of biological microstructure and is really helpful in clinical diagnosis and biomedical research. We want to extend 2D classical techniques into 3D using micro-CT to non-destructively image entire specimens. Unfortunately, the preparation protocols for routine histology mount tissue on plastic cassettes, which cause streak artifacts in micro-CT. We hypothesize that these artifacts are caused by beam hardening, photon starvation, and edge effects from using the periphery of the cone beam. To optimize our imaging protocols, we scanned an empty wax block at different accelerating voltages and mounting angles, and we used the standard deviation of the wax gray values as our quantification of streak artifacts. So we found that the best practices for on-cassette scanning with fewer artifacts was to use a high accelerating voltage, which reduced the beam hardening, and also tilting the specimen, which evens out the amount of attenuating material throughout rotation. Post-processing with Fourier bandpass filtering removed a lot of the artifacts, though we still get better quality from off-cassette scanning. We hope that this optimized protocol will help us have a more streamlined integration into routine histology. Thank you.
Hi everyone, my name is Elena and I am a research fellow in medicine at the University of Southampton. More than 25,000 operations to remove all or part of a patient's lung take place in Europe each year. To avoid revision surgery, it is crucial that the surgical team understands the full extent of lung tissue pathology while the patient is still on the operating table. Frozen sectioning is conventionally used to get histological information during surgery, and it takes about 20 minutes. Standard histopathology is always used as a backup, but it takes more than 12 hours, giving a result long after surgery is concluded. We have developed a micro-CT-based X-ray histology workflow that gives a result as quickly as frozen sectioning. It has the added benefit of providing three-dimensional imaging, and it is non-destructive. The 3D scan provides information about the whole volume that would otherwise be lost. We used pig lung for protocol development as it is very similar in size and structure to the human lung. On the left is one of these fresh lung biopsies in a standard container used to transport samples to the histopathology department. In the middle, you can see the micro-CT scan of that specimen completed in under 5 minutes. These data can then be presented using the semi-automated PDF reporting system, which is the subject of my other lightning talk today. To summarize, fresh lung tissue imaged by 3D X-ray histology in under 5 minutes has great potential to help support lung surgery in the future. Thank you for your attention.
The subfamily of braconid wasp, Myracinae, are composed of solitary cornubient endoparasitic wasps, which are biological control agent of tiny leaf miners moths, one of the most important group of agricultural pests. In the last decades, the non-destructive technology based on X-ray called micro-CT allows experts to visualize the external and internal structures of opaque objects such as insects with no need of sectioning. In this study, the female reproductive systems and its structures of Mirax caspiana was demonstrated using micro-CT. The specimen was scanned at UFO imaging station of Karlsruhe Institute of Technology light source at voxel resolution of 1.22 micron with 10x magnification. The study represents the female reproductive system of braconid wasp and demonstrates the first detailed 3D study of Mirax caspiana. High-quality volume rendering images and videos represent a notable advance in morphological structures study and are a helpful tool for future research and education.
Hello, my name is Kevin McKenzie from the University of Aberdeen, and we recently purchased a Pelco BioWeight Pro Plus system to help reduce sample preparation times for transmission electron microscopy. We've managed to reduce times for TEM from 2.5 days down to 2.5 hours, and for light microscopy staining of sections, we've managed to take the time down from 1 hour down to 10 minutes. So therefore, I've started investigating if we could actually use this preparation method for staining samples for micro-CT. So I've carried out some initial tests using a small bead pupa, and the stains I've used are 1% phosphotungstic acid and Lugol's iodine. So normally I would leave the samples for 1 to 3 days, and on the first test, I think I could probably reduce this down to about 35 minutes. So with the microwave system itself, we can set the wattage, so we're setting at 150 watts. This is under vacuum, and we do this for 25 minutes, and we have the wattage on for 5 minutes, then switch it off for 5, and so on. Once it reaches the end of the 25 minutes, we then add some fresh stain and repeat for another 10 minutes. And this is some example images of the section through the bee with iodine and PTA. So really, this is just to highlight another possible preparation technique that might work for micro-CT samples. And I'd like to say thanks to Amy Cooper for supplying the bees, and thank you.
Hello everybody, today I'm going to briefly present this collaborative work between my current institution, KTH, the University of Warwick and the University of Portsmouth, on the 3D deformation of the growth plate and growing bone. The growth plate is a cartilage structure located at the end of long immature bones where ossification and longitudinal growth occurs. Growth is regulated by many factors, including those arising from mechanical loading. However, information on the local mechanical state remains missing as traditional methods do not account for the complex structure of this region. Here we use X-ray compute tomography, in situ mechanical testing, and digital volume correlation to investigate the structure-function relationships in developing bone. Micro-CT images of the proximal end of immature tibia were acquired with the ToScA 9 atom in less than 5 minutes at different levels of compression and 32 microns voxel size. The growth plate was segmented and the thickness measured at each step to analyze its deformation, which reached approximately 33% at maximum load. DVC compute compressive strains accumulated in the growth region with the mineralized cartilage and new trabecula experiencing the highest strain. It can be seen how the immature skeleton efficiently transfers the load through the growth plate. Finally, we will be using high-resolution micro-CT and in situ mechanics to investigate such strain concentration in the mineralized cartilage and the newly formed bone at tissue level, to further explore its role as a mechanical stimuli during long bone development.
Hello, I'm Shiva Shrini, PhD candidate studying cementitious material imaging at the University of Malaga. Portland cement is the most used construction material, which has very complex microstructure because cement performance is controlled by its phase and composition and microstructure. In particular, the pore network play really critical roles, and also the cement's porosity affect the mechanical properties and durability as well. The chemical and the hydration changes in a PC binder affects the performance mainly because of the binding properties of the main component, which called CSH gel. And all of this is because of the water to cement ratio, which here we analyze the porosity in the PC paste using the laboratory and synchrotron X-ray microtomography after 28 days of hydration. Therefore, with increasing the water amount, we'll expect the more pores, more hydrated materials, and the less unreacted cements. Despite the around 0.2 micrometer voxel size in all the used experimental setup in this research, excellent spatial resolution and slightly better contrast with the synchrotron experiment serves as a reference and to show the limitation of the tomography approach as well. Meanwhile, the volume percentage of the constituent material phases have been in the order of the 80% of the reacted and 20% of the unreacted material for both laboratory and synchrotron experiments.
We present here our recent work on the foundations for routine 3D X-ray histology in Southampton. 3D medical imaging is commonplace, such as this conventional clinical chest CT. Yet microscopic tissue structure analysis remains overwhelmingly wedded to 200-year-old practices of microscopic 2D examination of tissue sections. For conventional 2D histology, tissue samples are embedded in paraffin wax, cut using a microton, mounted on a glass slide, dewaxed and stained for visual inspection under a microscope. Here we introduce 3D X-ray histology, which is based on soft tissue optimized micro-CT. It bridges the gap between low-resolution 3D clinical CT and traditional high-resolution but 2D histology, yielding details comparable to 2D optical microscope sections, but for the whole tissue volume. 3D X-ray histology can be seamlessly integrated into conventional histology workflows. It allows for non-destructive 3D imaging of tissue microstructure, resolving structural connectivity and heterogeneity of complex tissue networks, such as vascular networks or small airways in the lung. Applicable to a wide range of soft tissue types, the technology will open new research areas and it can translate directly into next-generation clinical image-based diagnosis. Thank you very much for your attention and looking forward to collaborating with you.
Hello, my name is Elaine and I'm speaking on LinkedView, a tool for visualization and annotation of correlative images. So correlative imaging uses several techniques on a single specimen, and these images provide different but complementary information about our specimen. The images are often at different spatial resolutions and dimensionalities, and though there's lots of software that will handle our microscopy data, none of them are specifically made for correlative images. So we would want a viewer which is user-friendly, compatible with our other image processing workflows, provides annotation tools, and is easily customizable for our individual needs. So we made linked view, which is based in Fiji. Here we are using an example data set with micro-CT and histology. You can match the displayed regions in all modalities. Here we've got the 3D projection on the left, histology in the middle, and single slice micro-CT on the right. You can transfer annotations between the images, which is especially helpful when you have features which are only visible in one of the modalities. And you can also export the cropped regions at their native resolutions. So here we've got the single micro-CT, we have the 3D projection, which has an interesting blood vessel, and also the histology image at its native resolution. Linked view is available open source. You can download it at the link below.
Hello, my name is Elena and I am a research fellow in medicine at the University of Southampton. In our X-ray histology facility, we use micro-CT to produce three-dimensional data of biological specimens. These data are then shared with biomedical researchers and clinicians who are often unfamiliar with this technology and may not have the time, expertise or resources to process and visualize them. This created the need for a data reporting system that assumes no prior user knowledge. For that purpose, we have developed a semi-automated PDF reporting system, which is directly linked with our custom-built XRH sample management system. The PDF format was selected to ensure cross-platform and multi-software compatibility. The first page of the report contains information and photographs related to the sample. The second page shows a central slice of the scan with the most relevant scan settings and a link to an online video slicing through the stack. Subsequent pages have thumbnails and links to other video visualizations of the sample. A final section contains useful links, resources, contact and acknowledgement information. By bringing together sample information and images in an easily accessible form, users can appreciate and assimilate the micro-CT data of their samples. Thank you for your attention.